Okay, I'm very excited to be here, and today I'm going to be talking about the new consensus protocols for ThunderCore's mainnet. As we all know, in all these decentralized cryptocurrencies, we want to keep a public ledger, and the core abstraction we need here, using the terminology of distributed systems, is called state machine replication, and this is often referred to as a blockchain or consensus. And in the state machine replication protocol, we have a set of nodes. In this case, we have Ethereum nodes. And these nodes are trying to agree on a linearly ordered log of transactions. Okay, there are two important security properties that we care about, namely consistency and liveness. So consistency says that all of the honest nodes must agree on the log. Okay, it could be like the network has delay and your network is a little bit faster than mine. Nonetheless, at the end of the day, we have to agree on what this linear ordering is. Now, liveness says that whenever you buy coffee, your transaction should be incorporated in every honest node's view fairly quickly. It's not like you want to wait forever for your coffee. Okay, now if all of these nodes were honest and they correctly follow the protocol, then the problem would have been trivial. But what makes it really challenging is when some of these nodes can be compromised. Let's say they have malware, and now these corrupt nodes, they can deviate arbitrarily from the protocol. And even in such adversarial cases, we want to make sure that the remaining set of honest nodes, nonetheless, must satisfy these two security properties. Okay, so this is the problem we are going to try to solve in the rest of the talk. Now, as it turns out, this is actually not a new problem. It has been around in the distributed systems literature for 30 years. But there are new challenges that arise because of cryptocurrencies. And because now we are taking this consensus to a really large scale. And at Thunder Research, we are trying to do exciting new research that overcomes these challenges, right? So some of these challenges include things like economics and incentives, and how to rethink and have new mathematical models to study consensus on a large scale. And in this talk, I'm going to focus entirely on the scalability challenge. And to kind of illustrate how bad the situation is, right? So this is the Ethereum transaction fees over time. I guess by now everyone knows, back in December 2017, there was this crypto kitty game. It's a kind of like a toy game in some sense in comparison with social network games or traditional mobile games in terms of daily active users, and yet this single game alone was able to overload the entire Ethereum platform. And this is how bad things are. And you may ask, okay, why are things so slow today? And the reason is because of the consensus, right? So there are multiple bottlenecks in the system. And today, the first bottleneck you encounter is the consensus bottleneck. And the performance you are seeing here is the consensus performance. So therefore, in order to scale up these cryptocurrencies, the first hurdle we have to overcome is to scale up these consensus protocols. And that's what I'm going to talk about today. And more specifically, I will first have a quick review of the Thunderella paradigm, which is kind of the basis of ThunderCore version 1 of the protocol. Like some of you may have heard of the protocol already. In that case, like I ask you to bear with me for a little while. But more excitingly, in the second part of the talk, I want to focus on the new developments, ThunderCore v2. And if you stay towards the end of the talk, I have an exciting announcement at the end of the talk. Okay, so let's first begin with the Thunderella paradigm. And the scenario we are considering is the following, right? So the guy in the middle, I'm going to call the guy a leader or proposer, and we also have a committee of voters. So everyone else is a voter. In this talk, I'm going to assume that the voters have already been selected through proof-of-stake mechanisms, and the set of voters can rotate over time. Now, I'm giving another talk at 10 a.m. And actually, the talk is joint with Chris Wang, our CEO. And in that talk, I'm going to talk about how to select the committee. So for this talk, in order not to be spoiler, I'm going to leave this intentionally mysterious. So I ask you to assume now that the committee and the leader have already been elected. I will describe a very, very simple consensus protocol, very natural protocol, and I will ask you to think about what this protocol can achieve. So let's begin with the protocol. And this is kind of like the most natural idea you can think of. First, the proposer is going to make a proposal. the proposal contains a sequence number and a batch of transactions, right? So typically we call the batch of transactions a block. A block is merely a batching technique. For simplicity, in this talk, I'm just going to assume we confirm one transaction at a time instead of one batch at a time. Okay. And now what does the sequence number do? The sequence number is going to determine where in this very long linearly ordered log this transaction is going to land. Okay, so now the leader in the center makes a proposal. Of course, everyone's going to vote once they hear the proposal. And the vote is basically a signature on the proposal. Very simple. If you are honest in this case, remember that the leader proposed an orange transaction in this case. So if you are honest, you would vote for an orange transaction, and you would cast an orange vote. Like some of these nodes can be corrupt, right? Like in this case, Loki is corrupt. And if he's corrupt, he doesn't have to follow the protocol. In this case, he voted for two blue transactions. He doesn't even have to vote for a single transaction. Okay, so after we vote, what do? We wait. We wait until we hear enough votes, right? So everyone waits until they collect 3/4 votes on the same transaction. At this moment, we have enough confidence because enough people have been saying, okay, this must be the transaction, and now I'm going to confirm this transaction. So that's the extremely simple protocol. And the most important thing, before that, let me call a collection of 3/4 votes a notarization, right? So from this point on, a notarization always means a collection of 3/4 votes. The most important thing for this very simple protocol is that honest nodes always vote uniquely at every sequence number. So what does this mean? At every sequence number, if I'm honest, I'm going to wait until I hear the first proposal from the leader, and I'm going to vote on that proposal and only that proposal and nothing else. And with this invariant in mind, I can give you an extremely simple consistency proof. Okay, and how does this work? So in this picture, imagine there's a set of blue nodes that have voted for the blue transaction, and there's a set of orange nodes that have voted for the orange transaction. And what I want to prove here is that it must be the case that the blue must be equal to the orange. These two transactions must be the same if they both collect many votes. I'm going to assume that the adversary controls less than half. Okay, so now let's consider these two sets, the blue set and the orange set. And my claim is that their intersection must be large. In particular, the intersection must have majority number of nodes. And the reason of this is very simple, because these two sets individually are large, and in total there are only n nodes, right? So the intersection must be large. And remember, the adversary controls less than half, and it must be the case that there must be an honest node in this intersection. And remember what I said about the honest node, right? The honest node is going to vote uniquely at every sequence number. And the only explanation, therefore, is that the blue transaction is equal to the orange. So there is our consistency proof. Okay, so let's take a step back and think about what this very simple protocol can achieve. I have proven to you that when we have honest majority among the voters, then we can achieve consistency. And the consistency follows no matter whether the leader is honest or corrupt. Even when the leader is corrupt, we still have consistency. So that's the nice thing. But the drawback of this very simple protocol is that we kind of need a stronger condition for liveness, right? We have to trust this central guy for liveness. Like, for instance, if this benevolent leader, that's the proposer, right? If he drops offline, he stops making proposals, or if he makes different proposals to different people, then we don't have liveness. Okay. So that's kind of unfortunate, and in a decentralized consensus protocol, you don't want to rely on the central guy for liveness. What we really want to achieve is to be able to achieve both consistency and liveness under honest majority and get rid of this stronger assumption. So how can we accomplish this? And we have a really simple idea for fixing this problem. Now, before I talk about our idea, in classical consensus protocols like PBFT and Paxos, this is achieved through what's called a view change mechanism. A view change mechanism is kind of like a recovery mechanism. In all these classical protocols, like the view change is rather complicated, but our idea is extremely simple. So here's the idea. Remember, I talked about the single round voting protocol, right? So from now on, I'm going to call this voting protocol a fast path. But now I'm going to combine a fast path with a slouching. So what is a slouching? Think of any blockchain that achieves both consistency and liveness under honest majority. And for the sake of today's talk, we can imagine the slouching is Ethereum. Like Ethereum achieves both consistency and liveness under honest majority in terms of computing power. But this doesn't have to be a proof of work slouching. It can also be a proof of stake slouching. So anything that achieves both consistency and liveness under honest majority will work. OK. And the idea is that when the fast path is behaving normally, we are confirming transactions really fast on the fast path, right? And we just let the fast path do its work. However, whenever the fast path fails, we are going to try to fall back to the slouching and use the slouching as a recovery mechanism. People can reach agreement on the slouching, and then using this mechanism, they can, for instance, discuss how to re-elect the leader on the fast path. OK. And the very nice thing about this paradigm is that we can achieve performance and decentralization at the same time, right? Because almost all the time, you are seeing the fast path performance. Like all the transactions get confirmed on the fast path 99% of the time. Very little data gets written to the slouching. Like only some metadata gets written to the slouching every now and then. So you're not subject to the slouching's bandwidth, the throughput bottleneck. And when things kind of fail on the fast path, and in these rare circumstances, we use the slouching to recover. So since the protocol is backed by the decentralized slouching, we actually enjoy the decentralization of the slouching. So we have both performance and decentralization. OK, so now the question is, how do you actually combine the fast path and slouching? I'm kind of going to just talk about this very quickly. I won't go into the details. But the idea is that we need two mechanisms. One is a detection mechanism for people to agree that the fast path has failed. And the second mechanism is a fallback mechanism. Once we have agreed that the fast path has failed, we have detected and agreed upon fast path failure, we are going to use a fallback mechanism. So we now switch to the slow mode, and we can use the slouching to reach consensus again and discuss how to re-elect the leader. OK, in either case, both for detection and for the fallback, we need to use the slouching as a consensus mechanism and reach agreement on the slouching. OK, so let me kind of skip through the details of this fallback mechanism. But what I want to say is that once we have this paradigm of combining the fast path and the slouching, the very nice thing we can achieve is this new property called optimistic responsiveness. OK, so recall that we want to achieve both consistency and liveness under honest majority. And now we can, right? We achieve both consistency and liveness under the yellow set of conditions. And under the stronger orange set of conditions, we can get fastness. In other words, when the leader is honest and online, and moreover, when 3/4 of the committee are honest and online, then we can confirm transactions very fast on the fast path without ever seeing the performance of the slouching under normal circumstances. OK. So this is a very simple protocol. Just to quickly recap, the idea is when things are good, we have a single round of voting to confirm transactions on the fast path, right? Just propose, vote, propose, vote, propose, vote, nothing else. That's not the end of the world, because we can always fall back to this reliable slouching to recover. So that's kind of the two-sentence recap. And recall what I said about the fallback mechanism, right? So when we want to use the slouching for fallback, we have to do both detection and fallback, and both rely on the slouching to reach consensus. And what this means is that if the fast path fails, we are going to suffer from the slouching's confirmation time in order for the protocol to continue. So if we use Ethereum as the slouching, which is what ThunderCore is doing right now, this is going to be a slow process. In particular, the slouching's confirmation time is about 10 minutes if we use something like Ethereum or Bitcoin. And this is kind of bothersome because there's a large gap between the fast path performance and the slouching. Although this fallback shouldn't happen very often, maybe it should happen once every year or something, the fast path shouldn't fail that often. nonetheless, whenever it fails, like you don't want to see this long delay to switch accelerator, to switch the proposer, right? Because the service will be disrupted during this fallback period. Okay, so how can we fix this problem and make the protocol better? And this leads to the second part of the talk, which I'm very excited about. We now have these new consensus protocols called Pili and Pala. And these protocols allow us to be able to switch accelerators on the switch proposer on the fast path seamlessly with no delay. And in fact, what this means is that we are now running a full-fledged consensus protocol on the fast path with both consistency and liveness. Okay, so I will explain what Pili and Pala is. In fact, Pili and Pala are two protocols from the same family of protocols. It's a new paradigm for constructing streamlined consensus protocols. Pili works in what's called the synchronous network model, and Pala works in what's called the partially synchronous network model. What we actually implemented is actually the Pala protocol, but for simplicity, today I'm going to explain the Pili protocol. But Pala is very similar. Okay, so how does the protocol work? Really simple. I have actually only one slide. So here's how it works. Imagine that time progresses in epochs, and let's say the network round trip is 1 second, and I'm going to define every epoch as 2 seconds. So 2 network round trips. In every epoch, what happens? A proposer is going to make a proposal in this epoch, and the proposal will extend the freshest notarized chain the proposer has seen. Okay, I'm going to take the longest, freshest notarized chain I've seen and propose the next block, if I'm the proposer for this epoch. And then when people receive the proposal, they're going to vote if certain nice conditions are met for the proposal. And the conditions you check are really, really natural. Number one, you want to make sure that the parent chain the block extends from is already notarized. And number two, you want to make sure that the parent chain is not too stale, like the parent chain ends at a reasonably fresh block. So if these two conditions are met, I'm going to cast a vote for this proposed chain, or rather this proposed block. And when the block gains majority votes, it becomes notarized. So notice that in this case, notarized doesn't mean final. Okay, so what is final? For the block to become final, I have to be a little bit more patient. I'm going to wait, and let's say at any point of time, I see some chain that's fully notarized, meaning every block in the chain is notarized. And now if this chain ends at 6 blocks of consecutive epochs, and moreover, I haven't seen any conflicting notarization at these 6 epochs. Now I'm going to chop off the trailing 5 blocks, and the prefix is final. So that's the entire protocol. Extremely simple, and the really nice thing about this protocol is that the entire protocol is just propose, vote, boom, 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 confirm, confirm, confirm. Nothing else. It's just a single propose, vote paradigm. And you know, classically, when we want to do a consensus protocol like PBFT Paxos, we have to have a view change mechanism to rotate leader. But here, like basically every epoch can have a different leader. So you may wonder, okay, now where's the view change, right? Because it's not clear here where the view change is. And that's the cool thing, because like the key insight here is that we figured out the view change doesn't have to be so complicated like in the classical protocols. It can be embedded in the same propose vote paradigm. So the whole protocol is just propose vote. And that's the really cool thing about it. And as you can imagine, like right now we have our fast path implementation, which is kind of like propose vote. And it's very easy to upgrade this implementation to this full-fledged consensus. And all you have to do is you have to be a little bit more patient. You chop off more blocks at the end before you finalize. And you have to check a couple more conditions when you vote. And that's it. OK. So if you add a couple more touches to the protocol I just described, you can achieve additional cool properties. optimistic responsiveness and best possible partition tolerance, right? I'm not going to try to go into the details here. The first is a performance property, and the second is a robustness property. And we have papers online that describe our protocol, both from a implementation perspective, like the practical version, and also we have mathematical proofs and theoretical modeling in this set of papers. Okay, all right. So the final question we have to answer is, okay, now that our fast path is a full-fledged consensus, do we still need the slouching? I mean, I guess the answer is yes, because nonetheless, the slouching is going to be more decentralized than fast path, right? The slouching can have a larger set of nodes, and these nodes on the slouching can have slower performance. So let's say the slouching is going to provide a decentralized monitoring and auditing mechanism for the fast path. And under extraordinary circumstances, let's say the committee on the fast path is entirely corrupt, even under these circumstances, we can use the slouching to perform reconciliation and recover. So that's the idea. Okay. So I'm going to try to conclude my talk with a very exciting announcement. So today, we actually just released the Pala open source on GitHub. And this is the URL. You can go and test it out. And this is work done at Thunder Research. And I would like to particularly thank Chao Hao Lo for leading this implementation effort. And ThunderCore is going to integrate this Pala consensus protocol into the mainnet implementation very soon. So it will be incorporated into the next release of the mainnet. OK. So that's the end of my talk. Thank you very much. We have launched mainnet. And if you are a dApp developer and you're a blockchain user, you should come and try out our blockchain. Thank you.